We're now prepared to extend our results into multivariate calculus. And in multivariate calculus, you can think of the analogy of finding areas to that of finding volumes. And so here we have a surface. It's a flat surface, f of xy equals 4. This is parallel to the xy plane. And so we can see this green surface here. And suppose we bounded the surface over the interval. And you'll see us using this notation R that stands for region. And the region that we're interested in finding a volume over is x from 0 to 4, y from 0 to 5. So now the difference is we need a boundaries for x and we need boundaries for y because we have 3 dimensions. What would be the total volume under the surface over this set of boundaries? Well, the way I want to think about this is if this is my x-axis here and this is my y-axis over here, then I want to basically look at the boundaries of this region, and we'll just say this is that's about 0 to 5, and then 0 to 4 would take us over here somewhere. And the way we want to be able to think about this is we have a region underneath here, and let me just go ahead and shade this. This region here is the two-dimensional xy plane down at the bottom, and then this region has a height as well, and we can think about the height of this region as where the curve, how tall that curve is. So we see that if we were to kind of sketch this in a slightly different way, that we have a two-dimensional region like this, and that this thing has a height of 4 units. So let me try my best to draw this. So here's my attempt at that, and we see that if I think about this as x equals 0 over here and x equals 4 over here, and I can think about this back portion as y equals 0 to y equals 5, and then the height of this is f of xy equal to 4. So we know that the volume is going to be length times width times height. And my length, doesn't matter which one you call length and which one you call width, but we'll just say length is 5. The width is 4, so that's just the area of our base right there. You can think about this as that area of our underlying region in the xy plane has an area of 20 square units, and then multiplied by the height, which is this constant 4, comes out to 80. And we haven't given this any specific units, so we'll just say units cubed, because we have units of length by units of width by units of height, gives us 80 cubic units total. So what we're going to want to do is we're going to, when we set these problems up, we're going to want to sketch the region that we're dealing with. So here, what I'm going to do in this xy plane is now pretend that we're looking down on the xy plane. We've oriented so that the z-axis is right here coming up at us, right in this corner. And we know that x goes from 0 to 4 and y goes from 0 to 5. And so the region is going to be this underlying region in that xy plane that represents the region over which we want to find the volume. Of course, if we expanded this region, we'd have more volume if our surface had a constant height of 4. So what we can call this is we can call this R, and R is that region x between 0 and 4 and y between 0 and 5. Great, so suppose we make our function more diverse and say that we want to know the total volume beneath the surface, f of xy equals x squared plus y squared over, we'll just say that same region. So now instead of having this flat surface like we do here, we could have a surface that is actually parabolic, or a paraboloid of sorts. So now imagine that this surface here, so to help us think about what this is going to look like, how could we possibly find an area under a paraboloid? Let's go ahead and take a look at this cool visual aid app that's going to help us see what it is that's going on. So here we have this three-dimensional surface. We see that that's a paraboloid, and we see that this thing continues to go up in all directions as we move further away from the origin. What we have here is just over the region 0 to 4 and 0 to 5. So you can kind of see what that would look like if we looked at it from below. Excuse me, from above, or what it would look like below if we looked at it from above. And we can see that this is our x-axis, 0 to 4, and this is our y-axis, 0 to 5. And we're looking down into the paraboloid. So you can see we're looking down into it. And if I were to continue to zoom out, you can see that that paraboloid kind of expands on forever. And you see that it has some really tall heights over here, especially in the corner where x is 4 and y is 5. But again, when I look down on it, what I see is that region R. And here I have a two-dimensional plot of that region as well. And so in order to estimate how much, let's say, how much rice can you stick underneath how many rice grains can you stick underneath this surface if this is your storage space, your storage facility? What we want to be able to do is we want to, first of all, break this up into, instead of a series of rectangles, we're going to break this area up into rectangular prisms. So you can see that these are almost like French fries. I like to describe them as French fries that have different heights. And the height of each French fry, for example, this guy here, that French fry its height is based on the center of that region. So if that little rectangle right there is for x equals 2, y equals about 1.5. So that would be x equals 2, y equals 1.5. This is the rectangle that we're talking about right here. And that guy has a specific volume associated with it. Now what we want to be able to do is we want to add up all of these volumes. But you can see we're getting a lot of underestimate, overestimate in certain places. So one thing that we could do is we could actually, first of all, look at this with only a small number of rectangles. So imagine that we just pretended that whatever the height of that paraboloid is right at the center of that rectangle, that's going to be our uniform height all the way across. Now we know that that's not true because as that paraboloid moves upwards over here in this corner, that paraboloid is going to be perhaps taller, especially as you move further away. So the paraboloid here is going to have a really tall height, but we're just estimating or approximating the height of that paraboloid by looking at what is the height of x squared plus y squared when x is 2 and y is 2.5. There are lots of different ways to do this. You could use one of the 4 corner points, but the left-hand sum, right-hand sum doesn't really quite work because there are really infinitely many points within each rectangular region. So we could have approximated the height of that paraboloid at x equals 0, y equals 0, but as you might imagine, that would be a rectangular prism with 0 height, because whenever you put 0 in for x and 0 in for y, you're going to get 0 as an output. So your estimate based on the height of the paraboloid at the origin would give you a volume of 0, which is not incredibly useful. So this method in this applet uses the center point of every rectangle. So when you plug in x equals 2, y equals 2.5, you're going to get its height, which, let's see, 4 plus 2.5 squared comes out to 10.25. So basically we would say that this has an area of 4 by 5. So the area is still 20, much like it was in the plane example. So a base of 20 square units multiplied by a height of 10.25 units, that would give us the volume of this region. Now, of course, it's not going to be a good approximation because you can see that we're wickedly overestimating all this stuff here that's inside of the paraboloid. That is not underneath it. But this stuff over here is actually below the paraboloid as that paraboloid continues to grow as you move both your x and y coordinates further into the first octant. So I can change the number of, I can slice this up and basically just break this up into 2 rectangles in the x direction and keep that 1 rectangle in the y direction. And you can see that that's going to do a little bit better. We're going to get the height of the paraboloid at 2 points, which is going to give us 2 separate volumes that we'll then add together. But why stop there, right? We could break this up into a set of a 2 by 2 rectangular grid. And the further we continue to break this up, now this app kind of starts to get a little clunky because it's doing a lot of work, but you can see here that as we break it up more and more and more, those French fries seem to have more and more of the shape of that paraboloid. And as you get more and more, but again, this app kind of clunks out, then we're going to get a much better approximation of that volume. Oh, there it goes. That's a little bit better. So you can see that the volume, or if we added up just the volume of every one of these French fries, however many of them there are, well, 19 times 13, that's how many rectangles we have in there, and we computed the volume of each of those little rectangles and added them all together, we would get an approximation for the volume under that paraboloid. So let's take that same approach for this example. In our two-dimensional drawing, we basically said that we were going to look at this from x equals 0 to x equals 4, and from y equals 0 to y equals 5. And so we have this nice rectangular region, and we want to find the volume underneath that surface. So one of the things that we could do is we could actually break this up into different regions, like in the applet. So let's just say that we broke this up into 2 pieces in the x direction, and we'll just say, we'll say 2 pieces, we'll do 5 pieces in, no, we'll do 2. We'll do 2 pieces in the y direction as well. Now notice that these don't have to be rectangles that have the same, they don't have to be squares. In other words, this is kind of a poor drawing, but you can see that I have 4 rectangles here. And if I think about the area of each one of these rectangles, the area, we'll just label these 1, 2, 3, and 4. The area of each of these, of region 1, or rather, not area, but the volume. So let's write the volume is, well, it depends on where within each of these rectangles we want to approximate the height. It's not really going to matter for this example because the height of the surface is everywhere the same. But let's suppose that I picked on the center point inside of each one of these. So these are the center points, and I looked at the height at each one of these locations. So at this height right here, which I guess would be f of 1 comma, that would be the mid-range of between 2.5 and 5, which would be 3.75. That is going to equal 4. And the same thing here, this one will be f of 3 comma 3.75, and that also equals a height of 4. And this one here will be f of 1 comma 1.25. That height is 4. And f of 3 comma 1.25, that height is also 4. So to add up, to find all these individual volumes, we're going to, first of all, multiply the width, and the width of each is something we could call delta x. So I'll write this as delta x times the height, which would be, or sorry, length and width, delta x and delta y, times the height, which will be the f of xy at the point of interest. Again, I can label these xi, yj, and we'll do that here soon, but for now, since they're all uniform, delta x is 2, delta y is 2.5, so 2 times 2.5 is 5, that's the area of each one of these individual rectangles, multiplied by the height of that particular region, which is 4, this comes out to 20 cubic units. And for region 2, it's going to be the exact same thing. Delta x is 2, delta y is 2.5. We don't want to change delta x or delta y midstream. We want to keep those constant for the particular problem, but notice that delta y and delta x don't have to be the same. Multiply that by 4. Again, we get 20 cubic units. For 3, we get 20 cubic units. For region 4, we get 20 cubic units again. We're just multiplying 2 by 2.5, and because the height is uniform at 4, we're getting that same volume for each one of those French fries, so to speak. And this comes out to 20 as well, and we get our answer of 80 cubic units, just like we did before. So next we want to think about how do we work with summations in 3 dimensions, and how do double sums work? Because now we're not only going to have to add across all of the x's, but we're going to have to add across all of the x's for every instance of y. And we'll go ahead and do that in a separate video.